Stanford University.
Okay, well, welcome to Lecture 4 of Stanford CS 193P, fall of 2011. And before I get started today, I want to take a moment and just talk a little bit about a good friend of mine, someone very important in my life, who passed away yesterday. When I graduated from Stanford, the first job I ever got was an insanely great job offer from Steve. And I went to work for Next Computer. And, you know, the 8 years that I worked there were just nonstop awesome. It was an incredible place to work. And it was because of Steve and his passion, his energy. And the stuff that we built there, the technologies we built long time ago, I'm standing up in front of you each week and talking about them today, okay, 2 decades later, and it's still the cool, hot technology, and that is a testament, for sure, to Steve's vision. He had a passion for aesthetics. You know, to him, having it feel right and look beautiful were super important. I think for him, beauty, you didn't go to the museum or, you know, see it hanging on the wall. Beauty, you could get it when you went to go check your email, okay, or when you answered your phone, or went to your music library, or watched, you know, a movie like Toy Story. For Steve, the beauty, what he felt like was that he could bring beauty to people in their everyday lives, and I think that might be one of his lasting legacies. You know, in a world where capitalism reigns and the almighty dollar says what is good and what is not good, the fact that he built the most valuable company in the world based on that premise, you know, that to me bodes well for mankind. That means we value that, and it certainly is testament to Steve to be able to do that. I read an article a couple weeks ago in the New York Times. A bunch of brain researchers were doing like fMRIs and brain scans of people who use their iPhones all the time. And they were trying to match them up against known brain patterns. And I think they were expecting that it would show up that these people who use their phones a lot had brain patterns like addicts, right? Like we're addicted to our phones. But when they looked at the brain scans, it didn't match people who were addicts as much as it matched people who were in love, okay? And we love our iPhones. We truly, actually love our iPhones, which is really quite amazing. So when you go out into the world to do whatever it is you're going to do, whether you're sitting here at Stanford or whether you're out there on iTunes U, you know, Steve would, if he were standing here, would tell you value aesthetic as a top priority, right? Bring beauty to people in their everyday lives with whatever you do. And so that's pretty much what I wanted to say. And so now I guess I'll go on to try and bring some beauty into your lives with my demo, my lecture. I know you love my demos. So, all right, 2 parts today. Demo first, then lecture. The demo that I'm going to do is demoing what we talked about on Tuesday. And the lecture slides are completely new stuff that you don't need for this coming week's homework assignment, okay? So don't freak out at the lectures like, well, you know, that stuff that you're learning is going to be combined with next week for the homework assignment after that, okay? So by the time I'm done with this lecture, hopefully you'll really understand what we talked about on Tuesday, and you'll be all ready to do your homework, okay? So what are we going to do today? The demo, I'm going to take the calculator as it ended after the walkthrough, basically, in that state. And we will basically make it programmable. And the way we're going to make it programmable is we're going to add some API to the calculator brain that says, give me your program. So the program is just the combination of operands and operations up to that point in the brain. Okay? So we'll be able to ask for the program. Once we have the program, we'll be able to go back to the calculator class, and with class methods, ask the calculator brain class to run the program for us. In other words, evaluate the operands and operations. And also, we're going to have a class method that gives us a nice human-readable description of the program. Okay, that part I'm going to leave for your homework, though. So I'm just going to show you the running the program part. This is the stuff we're going to use in doing that. We're going to use ID both as a kind of a cookie, right, an opaque type, and also we're going to have use ID because we're going to have an array that has both strings and numbers in it, right, operations and operands. I'm going to show you a property with no synthesize, what a read-only property would look like. We're going to use introspection. I'm going to talk about mutable and immutable copying of arrays. We'll use a little bit of recursion. This is, computer science class, so hopefully you guys are comfortable with recursion, or you will be by the time you're done with this assignment. And what I do today will be an extremely helpful start for your homework, so you definitely are going to want to use this for your homework. All right, so let's switch over to Xcode here. Make sure that I have the right thing. Yeah, so here is our calculator brain. Hopefully you're extremely familiar with this, considering you just turned in your homework yesterday, for those of you who waited to the last day. So all we're going to do to this calculator brain, again, is add some API to capture the program, and then add some API, class API, to run the program and get a description of it. So whenever I'm going to add a new feature to my application, I like to start with the public API between objects. Okay, even if I'm not going to implement it all right away, I just like to understand how my objects are going to talk to each other. Now, in this case, the public API that I already have here on the right, the push operand and the perform operation, I'm not going to change those. So I'm going to make this backwards compatible public API change. All right? So I'm going to add this program API, but the old API is still going to work. And in fact, so much so that this entire demo, I'm only going to touch the brain. I'm never going to touch the calculator controller, the calculator view controller. And we're going to run it at the end, and hopefully, if I haven't made a mistake or something, it'll just work. Okay, everyone understand my goal there? All right, so I said there were two parts to this new public API. One is we want to be able to capture the program. Right? The program, again, is just the combination of operations and operands that have been typed since the last clear, let's say. Okay? So I don't have clear because this is the end of the walkthrough, so here it's since the start of the program, but you have clear, so in your homework it should be since the last clear. So I'm going to do this actually with a property. Okay, I'm going to have a property here. It's an ID, and I'm going to call it program. Now, a couple of things here. One is ID. Let's talk about the ID. Why am I making this an ID? Why don't I make this a new class, calculator program star, or something like that? Well, the answer is twofold. One, I want to show you how to use ID as an opaque type, as a cookie. So it's a great example of that. And two, because I might not want to introduce a whole other class into my public API. Right? Then I got to document that, and people got to know how to use that and all that. And so I'm just going to start out with ID. Now, that means whatever I return from this property, though, this is public, so whatever I return for this property, people using my calculator brain aren't going to know what it is. And that's good. That's what I want. Okay? That buys me future compatibility. I can change what this thing is, support newer versions of it. I could add features to my calculator brain, and all the people using my calculator brain, their code won't change. Okay? But there's a couple other things about this, too. I'm going to make this property read-only. Now, this property would be perfectly reasonable to be read-write. It'd be fine to get the property, and then at some later date, say to a calculator brain instance, set your property to be set your program rather to be this. That would be reasonable. But we're going to, for this demo, to make it a little faster, and also for your homework, just to make it a little simpler, let's just make this property read-only. So you can only get the program. You can't set the program in your calculator brain. You kind of set the program when you do push operand and perform operation. You're kind of programming it when you do that. But you can't just set the program all at once. Okay? So I'm just making that decision. Could change it in the future. And then I said there were two other things. One is I'm going to have a method run program, which takes a program and runs it. And it returns the double, which is that program's execution. Okay? Now, what does it mean to run a program with an RPN calculator like this? Really, what run program means is pop the top thing off the stack and give it to me. And if the top thing on the stack is an operand, I just get the number that's on top of the stack. So if I go 3, enter, 5, enter, 6, enter, and then get the program and run it, I'll get 6, because that's the last thing I put on the stack. There's really not much else you can do. But the interesting part is if the top thing on the stack is an operation, because then I have to evaluate that operation in order to return double, right? Does everyone understand how we're going to do that? Okay. The only other public method I'm going to have is another class method. Sorry. Oops, let's get our pluses right. Plus means class method, right? NS string description of program. Okay? And this is going to return a human readable, suitable for putting into the UI, in this case, description of the program. Now, notice that both of these methods take an ID, a program, right? Where does that ID program come from? It comes from people calling the program property, right? The getter for the program property. And so that's it. This is the entirety of the API. People can get the program, and then anytime they want, they can ask the class to run it. Okay, so they don't even need, if they have a program in their hand, they don't even need an instance of a calculator brain to run the program. They can ask the class to do it. Okay? So I'm doing this specifically because I want you to see the difference between class methods and instance methods. When we implement these class methods, we won't be able to use any instance methods or any instance variables. Okay? So you're going to see how that works. All right. So let's start thinking about how we're going to implement this. One thing is our current internal data structure, which you'll remember, is this stack of operands, totally insufficient to the task, okay, because it doesn't keep the operations. It only remembers the operands. And what's more, every time an operation happens, the operands get popped off the stack and go away. So we need a different internal data structure. An obvious one to do is, instead of a stack of operands, why don't we do a stack of operations and operands? In other words, the program. So let's call this program stack. Okay, so I'm going to change that to program stack. Now, I can't just rename this and have everything work, of course. Computer science is a lot about naming, but it's not that much about naming. Okay, we actually have changing the semantics here of this stack. Now this stack means both things in it. So let's go ahead and change this stuff, our synthesize, and we still need our getter, and we still want to do lazy instantiation of this thing. So let's do that. All right, so we got all that. Oops, there's underbar. Okay, so now we have our program stack. We renamed operand stack to program stack. Oops, sorry, this needs to be program stack also. And now you can see we have errors in our program, and that's because we no longer have self.operand stack, and yet obviously we're using it. So what I'm going to do is I'm going to look at every place we use self.operand stack, and I'm going to try and replace it with self.program stack. But when I do it, I'm going to not just copy and paste. I'm going to look and see if the semantics are the same, okay, or not, or whether I need different code. So let's look at this first method here, push operand. Here we take the operand stack and we push the operand on there as an NS number object. I believe, unless I'm mistaken, that the program stack has the same semantics, because all we're doing in the program stack is we're pushing the operands and the operations on there, okay? And so it seems perfectly reasonable to me to just change this to program stack. All right, and so when you push operand, it's just going to push the operand on the stack. Okay? Now, we're going to have to be careful. We can't just start popping them off later, so we're going to have to be careful about that, but we can at least push it. Now, how about perform operation down here? Let's skip pop operand for a second. How about perform operation? This one, I claim I can just say self.program stack. Add object, which is push, the operation. Okay? So I'm just going to push the operation on the stack. So my program stack, I push operands on, and I push operations. But you notice the return value here of perform operation. It returns the value of executing that operation. So I need to do what? Run my program here. Right? So I could say calculator, this is a class method, so calculator brain run program, self.program, right? That seem reasonable to everybody? Right? I've got this method right here, this self.program. I haven't implemented it yet, but I have it. And I've got run program right here. So to perform an operation, why don't I just put the operation on the stack and then run it and return the value? Okay, we've got to say return here. Make sense? Any questions about that? All right, so that's super simple. Kind of have this junk down here. We'll leave that there for now. Pop operand, that's really not going to work anymore because it's popping things off the operand stack, and we don't really want to do that. That way we want to run our program instead, so I'm just going to actually get rid of pop operand. Okay? All right, so we're getting there. So far, our implementation actually looks simpler by going to this, which is remarkable considering it has quite an extra feature, which is the ability to tell you what the program is so far. So now let's go look at our property over here, program, to get the program. So I'm not going to synthesize it. So this is a property I'm not going to synthesize. I'm just going to implement the getter. Okay? And as long as I implement the getter, then I'm satisfying this read-only property. One thing about read-only properties, you don't have to implement the setter because they're read-only. Okay? So all I need to do is implement the getter. Now we have to ask ourselves, what would be a good thing to return? What kind of cookie could we return to people that would capture the essence of the program that they could then later give back to us and we could go evaluate? Well, it's completely trivial here. We're going to basically return our program stack. Okay? It's an internal data structure that represents that. But there's a problem with this line of code. Okay, there's actually two problems with it. One, self.program stack is internal state. Okay? We do not want to be handing out our internal state from an object through a public method. That would be very bad. Okay? Because even though it's an ID, somebody could get this thing, do introspection on it, find out it's a mutable array, start putting things in there, and totally blow us out of the water, totally break our internal implementation. So we absolutely can't be giving away our internal data structure. The other thing is the semantics of this property. When I ask for the program, I want the program at that moment. I don't want to get a mutable array that's being added to after that, right, adding more operations to it. I want a snapshot, basically, of the program. So we can solve both of those problems with this with one method call, which is to simply copy that NSMutable array. Okay? So copy does two things. One, it makes a copy so we're not handing out our internal state. It's a copy of it. And two, remember that copy sent to NSMutable array returns an immutable array. Can't be modified. So now the person who called it, who's got the program, even if they used introspection, they couldn't go in there and muck with it anyway. Okay? So that's it. That's all we have to do for program. Luckily, we have an internal state that's quite easy. We can just copy it and return it to give our program. Now, part of that is we picked good internal state, right? We designed our thing really nicely so that it's really easy to implement this because we knew we were going to support this API. All right. So next, let's do this description of program. Oops. String star description of program. And here I'm going to do this. Return, implement this in assignment 2. Okay? And I'll leave the rest to you on that one. How about run program, though? Let's, at this top level, when we're running this program, first of all, we need to get that program into a form that we can operate on it. Because right now, when it's passed to us, it is an immutable array. Well, that we can't really work on an immutable array. We need it being back to being mutable, essentially, so we can work on it. And also, we want to be careful that if someone passes in some random object, we don't crash. Anytime you have a public API that takes an ID, you want to use introspection to protect yourself against someone passing something wrong. Okay? So I'm just going to say, first I'm going to create a little local variable here called NSMutableArray stack. That's going to be our program stack. By the way, you could say equals nil here, but local variables that you create automatically start out 0 in iOS 5. They didn't in iOS 4 and before, but in iOS 5 they're 0. So we can just say NSMutableArray stack here. We don't have to say stack equals nil. And then I'm going to use introspection. I'm going to say if the program is an array, then stack equals the program. Oops, sorry. Let's make a mutable copy of the program. Okay, so now I have this local variable, stack, and again, I've done two things with that introspection. One, I've made sure it's an array, because I can't work on anything else. I give out arrays as my program. They better come back as arrays. And two, I've made a mutable copy on it so I can munch on it. Because the way I'm going to implement this run program is I'm actually going to consume all the things on the stack in a recursive method. Okay, so this is where the recursion comes in. So I need it to be mutable so I can consume it. Everyone knows that a recursive thing needs to be progressing towards the end case, and the end case for us is going to be an empty array, or at least we get to an operand and we stop. So now we need a method, and it's going to have to be a class method here, because I'm in a class method run program. So I need a class method that basically just pops the top thing off the stack and returns it. Okay? But if the top thing on the stack is a number, it's going to return the number. If the top thing on the stack is an operation, it's going to have to recursively evaluate it. So I'm going to create a little method here called pop operand off stack. Okay, and I'm going to return this. So this will be a little better. Okay? So now we just need to implement this. Pop operand off stack. Everyone cool with that so far? No question? Yeah, question.
So what happens if the thing that passed the program that passed in is not a array? Will it be nil and it will?
Yeah. So I did it this way also, so I want you to get comfortable with sending messages to nil and handling nil and how you program when sending things to nil does nothing. So the question is, what happens if the person passes something in here, the user of this, that's not an array? And what will happen here is this starts out nil. This is not going to be true. So by the time we get to here, this is still going to be nil. So we're going to be calling this class method with this as nil. So we better make sure that this class method handles the case of an argument of nil. Okay, and that's what we're going to do. Yeah, go ahead.
Is that thing going to style using in general, just like have it implicitly handle that, or what's the benefit of doing that versus explicitly?
I mean, the question is that the kind of programming style we do in Objective-C, where we kind of let things be nil and we just kind of implicitly handle that case? Or should we have a lot of if this equals nil, then don't call pop operand off stack, return 0 instead? And I think that's an art of programming thing, right? You're going to hear me use the phrase art of programming more and more as the quarter goes by, because programming is an art. You have a choice of how to do it. I personally am a believer that fewer lines of code are better. So if you can make your pop operand off stack be bulletproof to accept nil without having to do if, then, blah, 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 then pop operand off stack will be more robust, because if someone calls it in some other context and they actually pass nil, it'll work. And this code is simpler right here, because I don't need an if, then here. So it's kind of an art of programming, is the bottom line. Okay, so we need to go implement pop operand off stack. Important thing to notice here is that it is a class method itself, okay, because it's getting called from a class method here. So self here is the class, right? Make sense? So pop operand off stack. Now, what's the argument to the stack? It's not an ID anymore. Okay, we're going to take NS mutable array. And we have to make sure, and the compiler will help us make sure, that we pass an NS mutable array here, and we know that we do that here. One thing I forgot to mention, notice here, stack is statically typed, and mutable copy returns an ID. And it is okay to assign an ID to a static variable, and vice versa. Okay, compiler's not going to warn you or anything like that. So you got to know what you're doing. Luckily here, we know that program is an array. So when we make a mutable copy of it, it'll end up being a mutable array. Unfortunately, the compiler can't check that for us. We just have to know that. Okay? All right, so pop operand stack. This is where I'll do the double result equals 0 and return result. And we'll do it our little recursion inside here. So pop operand off stack, what does it do? It pops an operand off the stack. Okay? So let's start by popping the top thing off the stack. So I'm going to have a local variable here, top of stack equals stack last object. Remember, that's how we implement stack, by getting the last object. And if the top of stack is not nil, then I'm going to remove the last object. All right? Does everyone understand how that pops the last thing off our stack? Notice that I made this be type ID. Why did I do that? Anyone know? Why did I do that?
Either an NS number or an NS string.
Correct, because the top thing on this stack could either be an NS number that we pushed with push operand, or it could be a string that we pushed with perform operation. So when we pull it off, it's an ID because we don't know which one it is. And we have to go use introspection to find out which one it is. So let's do that now. So we're popping an operand off the top of the stack. So if the top of stack is an NS number, number, class, just a keyboard, I'm sorry, I'm not quite used to. Okay, if it's if the thing on the top of the stack is a number, then we can just set the result equal to top of stack double value. Right? Make sense? Because we're popping the operand off the top of the stack. It's going to be a little more complicated if the thing on the top of the stack is a string. We're going to do that next. But everyone understands that if the top of the stack is an operand, we can just pop it right off and that's the result. Everyone cool with that? Okay, but what if the top of the stack is kind of class an NS string? Okay, so we have to make the result equal something different here. Well, I'm going to go back down and get this code that used to be in perform operation, because that's exactly what I want to do, is perform an operation. So I'm going to cut that. Oops, sorry. Cut that and put this up here. It won't quite work as is. You can see a couple of things we're having errors with here. One is we're using this variable operation. I could change that to be top of stack, but to be clear, I'm actually going to create a local variable operation and set it equal to top of stack. Okay, and I'm just doing that for two reasons. One, to keep this code as similar as possible so you're not too freaked out by how much it changes. And two, to show you again that I can assign an ID to a static, and the compiler has no problem with this. But again, I got to know what I'm doing, so I want to do it right after introspection like this. Okay? So what else is this complaining about right here? It's complaining about pop operand, because pop operand was an instance method that popped an operand off the stack. We don't have that anymore. I got rid of it. Okay? So how are we going to pop an operand off the stack now? Sorry?
Recursively call pop operand.
Exactly. We're going to recursively call pop operand off stack. Okay? I'm just going to change every call to pop operand here to be pop operand off stack. So that one, that one, that one, that one, like that. Okay? So who said recursion is hard? It's so easy. That's all there is. Okay? We've satisfied all the things necessary of recursion here. We're always progressing towards an end case because we're always removing something off the stack every single time. Eventually, the stack is going to be empty, if nothing else. Like if we try to do too many operations, not enough operand, it's going to end. Or if we do all the operations that are on there, then you'll stop. Still might be stuff left on the stack, but we'll be done because of this end case, basically. One thing to make clear, you'll remember that in the old version of perform operation, we pushed the result back on the stack. We don't need to do that here, okay? Because we're consuming the stack as we go, and their operations are on the stack too. Okay, so we don't need to push the results and then go back. We are actually consuming as we go. So we don't need any of that. We don't need this. Okay? So that's all there is. Now, two other things I want to point out here. One is, what if this program that was sent to run program is an array, but there's something in it besides numbers and strings? Okay, what are we going to crash? What's going to happen here? We're going to return 0, exactly, because we're going to get here, we're going to take this object off the stack, let's say it's a button, okay, or a controller, or some random thing, and we only have two if cases here. If it's a number, we do one thing. If it's a string, we do another thing. There's no other else. So we're just going to return a result, which is this thing up here. So we do survive the case where someone passes us an array of junk. And that's important. Like I said, anytime you're going to take an ID that's supposed to be a cookie, you know, an opaque type, make sure you protect yourself. And then let's also look, what if stack is nil? Okay, we wanted to make sure we survived that case that we talked about earlier. If stack is nil, this is going to return nil. Okay, this is not going to get executed. This is not going to be true. This is not going to be true, so we're going to return 0 again. So we survived that case as well. So can you see how kind of rolling with the punches of nil can really make for clean code, right? We've got very simple code here. We don't have a lot of extraneous if this is nil, then do that, check that. We're kind of rolling with it. And the only if we really have about nil is this thing. We don't want to be trying to remove objects from an empty stack, you know, an empty array. That's the only if we really had to do. Okay? Any questions about this? So that's all we have to do. Okay? So the recursion wasn't so scary, right? And hopefully, if I type this all in correctly, this will work. So let's go ahead and run. Now, notice I haven't changed my controller at all. It's still using this old API right here, push and perform, and works fine. Okay? And so let's hope it's working. 3, enter, 6 plus, 8, divide, 9 times. You know, let's try 5, enter, 2, enter, 6, enter, plus, plus, divide. Working great. Okay? All right. Everyone understand that? So what you're going to do for your homework is you're going to take this modification that I made and apply it to your assignment number 1. I posted this code just for the calculator brain, so you don't have to type it in again, although it wouldn't be that hard to type in again. And so you're going to integrate this in, and then you're going to implement description of program. Okay, you have to do that. And most importantly, you're going to change run program and also the rest of your calculator brain so that you can not only push operands and perform operations, but you can push variables. So now you're going to have a programmable calculator with variables like x and y, whatever. And then your run program is going to have to change to say run program using variable values. You can take a dictionary where the keys are variable names and the values are just NS numbers with the value of those variables. Okay? So now hopefully by doing that, you'll A, understand this recursion because you're going to have to use it for description of program. And B, you're going to understand how to use NS dictionaries because the run program is going to take a dictionary now. You're going to have to kind of learn in general how to use the foundation classes. There's some stuff you have to do with NSSet in there as well. And hopefully you'll come out the other side where you're comfortable with ID, you're comfortable with all the foundation classes, and you're just more comfortable with programming in Objective-C. Okay? I put in some other required tasks in there for you to enhance the user interface and stuff like that, so it should be a lot of fun. Okay? So that's your homework that's due next Wednesday. And that's already posted. Okay, so that's it. That's all I had to show in the demo. And that is kind of the end of this segment. And now we're going to start some slides for the next segment of stuff we're going to learn. So let's go here. All right, so the next thing we're going to talk about is views. All right, so you've already used views. You probably don't even realize you've used views, but you have because UI button is a view, UI label is a view. And a view is just a rectangular space on screen. That's really, it defines a coordinate space. Now, it's a very powerful coordinate space. It has a lot of stuff in there to make it really easy on you. Okay, iOS kind of has this design paradigm, which is they're going to make it complex on their side internally so that it's really easy on your side. That's good for you. What does a view do? It draws in that rectangular space and it handles events in that rectangular space. Both are really easy to do. Okay. The view structure is hierarchical, as you might imagine. You can have views inside views. Any view only has one super view that is contained in, but it could have multiple subviews. The order of the things in the subviews matter because the things higher up in the array at 0 are in the back, and things lower down are in the front. Okay? And you'll see why back to front matters. And there is, I think UI window is a subclass of UI view. I can't even remember anymore. But the reason I can't remember is that UI window really doesn't matter in iOS. You almost never interact with the UI window. If you've programmed in other systems, you probably think UI window is important because you've got to put a window on the screen and all that. That's kind of all handled for you in iOS. What's important in iOS is views, all just about views. And the top level view, the highest view you're going to interact with is the view for the controller that controls the whole screen. Okay? And you're going to find out next week that we can have controllers of controllers. Obviously, we can have MVC, where the view part of an MVC is another controller. But usually there's a controller that has a view, which is the whole screen. Might be using other controllers to make the details of it, but this hierarchy, the view hierarchy, is almost always created in Xcode graphically, just by dragging things out. You can drag views inside other views and resize them and all that stuff. So that's how we do that. We'll see a demo of that next week. But you can make the view hierarchy in code. There's two important methods there. One is add subview, which is sent to a view to add a view to it as a subview. But taking a view out is not done that way. You don't ask that same view, oh, and now remove that thing I asked. You now go to the view itself and say, remove yourself. Okay? So some people sometimes get a little confused here, because this is a different paradigm. One, you're asking the super view to add the subview, and to take it out, you're asking the view to remove itself. Does that make sense? You'll hardly ever have to do that in this class. Maybe never. I don't know. I said that a view is a coordinate system, so we better define some types to describe that coordinate system. The base one is CG float. This is just a type def to a float, probably, or a double. You don't know, but you don't care. When you're programming graphically, you're always going to use CG float, never float or double. Then there's CG point, which is a C struct that just has float x and y. CG float, sorry, CG float x and y. There's a size, which has inside a CG float of width and height. Okay, some code up here about how you can call the C function CG whatever make to make one of these things. And then there's CG rect, which just has a origin and size, a CG point and a CG size inside, as you might imagine. Okay, so these are the four main types that we're going to use to be able to describe our drawing inside of our views. So now let's talk about the coordinate system. All right, most important thing to remember: the coordinate system in iOS is in upper left origin. It's not Cartesian coordinates, which is lower left, which is also the way the Mac is. It's in upper left. Okay, so increasing y is going down. So for example, if you had the point 400, 35, it would be far over to the right and a little bit down from the top. Okay. These units are points, not pixels. Okay. What's the difference between a point and a pixel? Okay. A point is like a typographical term. But what makes the only time the points wouldn't equal pixels on a device is like on the iPhone 4 Retina display. It has such high resolution, okay, that if a point equaled a pixel, then something you drew on it would be, a quarter of the size as something you drew on an old iPhone. Okay, so there is a property in UIView called content scale factor, and it will return how many pixels there are per point. But you're usually going to do all your programming in points. Okay? Now, just so that you learn this, next week's assignment, not the one assigned today, but the one that's assigned next week, is actually going to do something that requires you to know about pixels. But normally, you're not going to need to know about pixels. The iOS will handle it for you. It'll make the fonts really smooth if you have more pixels. It'll make arcs really smooth. So you don't usually have to worry about it, but you'll see in the assignment that you do, so that's why I'm mentioning it here. Views have three properties that are related to their location and size. Okay? One of them is called bounds, and it's this rectangle, and it is the drawing area of your view in your view's coordinate system. In your view's coordinate system. So when you draw in your implementation of a custom view, if you're creating your own view, you're not using UI button, but you're creating your own subclass of view, when you draw, you only use bounds. Do not use these other two inside the implementation of your view. Just don't do it. Okay? What are the other two? Center and frame. These are the center of your view and the frame that completely contains your view in your super view's coordinate system. So these are only used to position you in your super view. Everyone understand what I mean by that? Position you? They're just used to say where you are. If you specify the frame of a view, you're placing it in a super view, and that super view's coordinate system. That's different from the bounds. Now you might think, well, bounds and frame, pretty much the same thing, right? And the answer is definitely not. And why are frame and bounds not the same? The answer is because views can be rotated and scaled as well. So if you had a picture like this, you see how view B is rotated? Its bounds in there, 200 by 250 with the upper left corner. To view B, it looks like it's just in a normal rectangle. It doesn't know it's rotated. Okay, somebody else rotated it. So it's just drawing happily. But look at the frame of view B in view A's coordinate system. It's much bigger than view B because it has to completely contain view B, including its rotation. Do you see? So the bounds on view B is only 200 by 250, but the frame of view B, in other words, its containing rectangle in the superview coordinate system, is big, 320 by 320. Okay? The center point is 300, 225. If you accidentally used the center property inside view B, you wouldn't even be drawing in view B's bounds, right? It would be all off screen. It wouldn't even show up because the center is 300, 225, and view B only is 200 by 250. So can you all see the difference between frame and center, which kind of go together? If you set one, you're setting the other, right? If you set the center, it's going to move the frame. If you set the frame, it'll set the center. They match. They automatically are kept in sync. And the bounds, which is the rectangle you use to draw yourself. Cool with that? So people ask, what is view's middle? What's the red dot in view's coordinate system? Well, it would just be the bounds dot size dot width divided by 2 plus the origin, and the height divided by 2 plus the origin. That's how you would, if you were view B, that's how you'd find your center. Views are rarely rotated. I mean, you see the UI, you don't see a lot of rotated views, but they could be. And you do never want to write code that uses frame and center in the implementation of a view. You use frame and center to position them. All right, creating views. So most often, you're going to create views in Xcode. Like I said, you're going to, you drag out buttons and labels. That's you're creating views. How do you drag out a custom view? Okay, because when you create a custom view, you're going to subclass UI view to create a custom view, and it's not going to appear in the palette, right? The palette in the lower right where UI label and UI button is. You're not going to see my custom view in there, unfortunately. So what you're going to have to do is you drag out a generic view. If you look down in that palette, scroll up and down a little bit, you'll see where it says view. And you're just going to drag out a generic view. So now you have the view in there, but you want it to be your class, so you're going to go to the identity inspector in the upper right, where the attributes inspector is. One of the things there you can click on is identity inspector. And in the identity inspector, the very top thing in the identity inspector is the class of this thing. So if you clicked on UI button, it would say UI button in that identity inspector. And when you drag this out and you look at an identity inspector, it's going to say UI view. And there's actually going to be a pop-up there, because it'll know about your class if you've already created it in Xcode. Or if you haven't created it yet, you can actually type in the name of your custom class. So it's one of those pop-ups where you can pick from a pop-up, or you can type it in the same thing. Okay? So that's how you add a custom view. And now, the custom view, once it's in there, when it's in the storyboard in Xcode, it's not going to behave like your custom view because your custom code is not in Xcode. The actual code is not, the code that you're typing is in there, but the compiled code is not in there running. But you can still do some things with the view, like you can set normal view properties. Views have background color, for example. You could set that. And you can clearly resize it, and you could add other views as subviews of your view, or you could add your view as a subview of other views. So there's a lot of things you can do with the view, but that's how you add a custom view to your UI. You could, of course, also do it in code. And so how do you create a code, or create a UI view in code? You just use alloc and init. All right, it's like we talked about last time. And you can use alloc plain init. That would create a view with bounds and frame being, well, the frame would be 0, 0, 0, 0, 0, all 4 zeros. And the bounds would also be zeros. And then you could later set its frame to make it bigger, okay, or set its bounds. But the designated initializer for UI view, and the one we would use most often if we were creating code, is init with frame. We talked about this on Tuesday as well. And you just specify the frame of your view, and it'll create a view. Now, it doesn't add it to any view hierarchy. You still have to call add subview on some other view to get your thing added to a view hierarchy, but this is how you create it. So here's an example. Almost maybe I'll do this later in the quarter just to show you this, but not next week. Here I'm creating a UI label. So first I create a rectangle called label rect. It's 2020 from the upper left, 50 wide, 30 high. And then I'm just saying UI label alloc init with frame. UI label is a view, so it inherits init with frame. So that works fine. And then I'm setting the label's text to hello. And then I'm saying self.view, add subview, the label. Now, self.view, by the way, we haven't talked about that. We'll talk about it next week. View is an important property in controller. It's the controller's top-level view. Okay, every controller, model view controller I'm talking about here, every controller has a top-level view. We don't usually have to interact with it too much because we just drag things into it in the storyboard in Xcode. But it's a very important property on a controller, as you might imagine, is the containing view that contains all those labels and buttons that you added in your calculator, for example. We'll talk all about that next week. All right, so when would I want to create my own UI view subclass? I've been talking about the custom view. When do I want to do it? Well, I told you that views are for drawing and handling touch events. So you want to create your own UI view when you either want to draw something specific, right, different than drawing a button or label or whatever, or you want to handle touch events specially. Okay? Now, people often at this point ask me, well, can I subclass UI button? Because I mostly want UI buttons look and feel, but I want to, maybe make the touch events work a little different. And generally, I think the recommendation is not to subclass the built-in types. They're kind of the built-in subclasses of UI view. Generally, they are optimized for being dragged out in Xcode and used, not as much optimized for subclassing and overriding this method and not that method and what would happen in that case and all that. So I'm going to kind of steer you away from taking an approach to doing a UI that you think would require you to subclass these things. It's not impossible. It's an object-oriented program. You could do it, but I'm kind of steering you. So once you create your subclass of view, oh, and as I say up there, today we're only going to talk about drawing. Next week we'll talk about handling touch events in a view. So how do you draw? You got this subclass of view. It's incredibly easy. You just override this one method, draw rect. It takes a rectangle that it wants you to redraw, which you can ignore. It's a performance optimization to only draw in the rectangle it's asking. And that's it. You just draw. It says draw rect, you draw. Now, one important thing to notice about this, never, I don't put a lot of red on my slides, but when I do, you got to pay attention. Never call draw rect, ever. If you call draw rect in a homework, oh, you'll get bashed, okay? Because draw rect is not for you to call. The system calls draw rect for you. So you might ask, well, how do I tell the system that I want my view redrawn? And the answer is, you send it one of these two methods, set needs display or set needs display specifying the rectangle you want redrawn. And you can kind of think of it as set needs display sets a bit, and then at some time later, the system will come along and look at all the views that need to be drawn, put them all in the right drawing order, because remember, these things can overlap and stuff like that, and efficiently ask them to draw themselves as necessary. Okay? This is good for two reasons. One, it allows the system to optimize performance in terms of the layering and things like that. And two, it optimizes performance in that you might have, let's say, your setters for your custom view. Maybe you got a few properties. Maybe when you set something, it wants to redraw. Okay? So all your setters might say, set underbar, set my property, and then they might say self set needs display. I need to be redrawn because one of my properties changed. Well, if someone using your view calls 3 or 4 of those things, those property setters, it only redraws once, right? Because they're all just saying, yes, set needs display, set needs display, and then later it makes a pass and it draws once, as opposed to each of those setters saying, draw now, draw now, draw now, and the thing just constantly drawing. Okay? Drawing is expensive. Okay? If you think about what's happening when drawing, at the very least, you're taking a whole bunch of memory from one place and putting it somewhere else, i.e. from memory into the graphics buffer, from one graphics buffer to another one, or whatever. It takes, the processor's got to run some instructions to move all those things. Now, granted, modern graphics processors, man, they move those things incredibly efficiently. It's just unbelievable how optimized they are. But it's still very expensive. For example, in the calculator we did today, notice that when we perform an operation, we push it on the stack, make an immutable copy of the stack, turn it back around, make it mutable again, go process the whole thing to calculate the result. The amount of instructions to execute that is nothing compared to the amount of instructions it took to highlight the button that the person pressed on to make that happen. Okay? Now, I bring all this up because I want you guys to not fall into a trap that a lot of computer science students do, and even people out in industry who are writing code, is you see something that looks inefficient, and so you're going to dive in and optimize it. Okay? When you do that and you're not thinking about where the time is actually going, that's called premature optimization. Okay? Don't do that. You really want to think about the trade-off between, like, look at the code we wrote in the calculator. Wasn't that incredibly simple code? I mean, our push operation was 1 line of code. Our push operand was 1 line of code. Perform operation with 2 lines of code. The recursive thing to execute the stack was only like 2 or 3 lines. In fact, there's probably only 2 lines more than we had before. Okay? So that code was super clean. Now, granted, yeah, it's copying arrays, but we know copying arrays is fast. We know that the arrays are small. Okay? You're not going to have someone typing in 100 operations and operands there, likely. So trying to optimize that down and add 100 lines of code to really make that all really go fast is a complete waste of time, because you know this is only being executed by a very slow thing, which is touches on the screen. Now, I say very slow. It's all relative. Doing a touch on the screen is super fast. I mean, less than a millisecond. But the other stuff is even faster. These processors in these phones are super fast. Okay? But make sure you got the right balance when you're doing performance. Everyone understand where I'm going with that? And I'll say that again a few times. We do not want to see code in your homeworks where you've added 50 lines of code to optimize something that is less than 1% of the processor time to do a certain task. Okay? And in fact, I'll use this opportunity to say another thing too, which is the programming credo I live by, is that the line of code that is the most elegant, has by far the least bugs, is the easiest to write, is the easiest for someone else reading your code to understand, that line of code is the code you never write. Okay? Fewer lines of code is better. That's what programming elegance is about. Okay? Designing your data structures and the way you approach things so that you have fewer lines of code. Not more, fewer. All right, I'll say that a bunch of times too. All right, so I have this drawRect. I need to implement drawRect to make my custom view draw. How do I do that? And the answer is you use the core graphics framework. This framework is the main framework that you're going to use that is not object-oriented. Okay? It's C APIs, but it's pretty straightforward to use. The fundamental concepts of the core graphics framework are that you create a context, then you create paths out of lines and arcs and things like that. You set the colors and fonts and line widths that you want, and then you stroke or fill, or stroke and fill, that path. Okay? That's how you draw. Now, I'm going to talk about drawing images and text because they're primitives in iOS. I mean, drawing text is the same thing, drawing a bunch of arcs and stuff, but it's a lot of really detailed arcs. But that's all done for you, of course. And drawing images is just copying bits. So we'll talk about how to do that, too. So I'm going to talk about all these pieces. So the context just determines where your drawing is going, okay? And so how you create the context defines where your drawing is going to go. Now, the great thing when you're doing drawRect is you don't even have to worry about this. Because when you get inside drawRect, you're going to call a function, a C function, that's going to give you the context that the system wants you to draw in. Now, the system might be printing right now. Okay? And when you print, you can find out that you're printing in drawRect and maybe draw your thing big, like 8.5 by 11 piece of paper big versus on the little screen. And in fact, you'd want to do that if you had a real app that could print. Take advantage of that new thing. But the context that you get, you're going to get in the same way. One thing to notice about this context, though, it's different every time drawRect is called. Every time drawRect is called, you get a different context. So never, ever cache that context like in a property or anything like that. Do not keep it around. It is different every time. Re-get it at the beginning of drawRect. So here's the function you call. This is almost always going to be the first line in drawRect, or one of the first lines, is CG context ref, which is a cookie. It's a void star. You don't know what it is. It's just an opaque type to you. It's not an object, right? There's no star there. CG context ref context equals UI graphics get current context. You're going to call that in your drawrect. Now you've got your context. Okay? That's all there is to it, to getting the context. Now that you have a context, you can use it to build these paths. So here I'm going to show you an example of building a path. You start with CG context begin path. You pass it that context you got. Then you can move around and add lines and stuff. For example, context move 2 point 7510, and then see context add line 2 point 160 150 would be creating that segment of this path, right? And then if I said move to 10 150, it would make another segment. Okay. Again, notice upper left is 0 0. This is not to scale, I guess. And then there's also CG context close path. That would close the path up back to its start. Okay? It's optional. You don't have to. You can have an open path, but close path, close it back up. Now, I kind of lied to you here because it made it look like as I was doing these, it was drawing. But in fact, doing this code above does nothing on screen. Okay? It creates this path, but it doesn't actually draw anything. So your screen would be still completely blank if you executed the code that's on there. And why is that? That's because you have to stroke or fill to make your path appear. And before you stroke or fill, you want to set some graphics context. So here I'm using a color to set the fill and another color to set the stroke. Now we're going to talk about UI color in a couple slides here. And also notice that these UI color, green color, set, fill, you don't specify the context. When you use the objects, you're only going to use 2 objects to draw, 3 maybe. UI color, UI font, and then NS string actually you're going to use to draw text. But we'll get to that in a minute. So here, when you're using the objects, you don't specify the context. The objects always assume you're using UI graphics get current context. Okay? It's only the CG context blah 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 that you specify the context and argument. So here I've set the fill and set the stroke. It still hasn't drawn anything. Okay? I have to call the core graphics function that draws, which is called CG context draw path. Okay? And it takes context, and the only argument it takes is this constant KCG path fill stroke in this case. There's also KCG path fill, and there's also KGCG path stroke. And that specifies whether you want to stroke the path and fill the path, which is what this is doing, or only stroke it or only fill it. Okay? So here I did fill and stroke, and so look, my triangle got stroked with a red color, and it got filled with a green color. Okay? So that's it. That's how you draw. You build these paths up, and there's a lot more than move to line 2. There's arcs and gradients, and I mean, I just want to show you how you do it. You're going to have to go read the documentation to find the function you want, and there's a lot to choose from there to draw. It's also possible, by the way, to build up a path and then save it in a path variable, CG path. Okay? So a CG path, so the functions are very similar to that, but instead of taking the context to drawing, you're taking the path that you're building up. And so then you end up with a path, and then there's another C function that you call that says take this path, this CG path that I built out of all those move 2 and line 2s, and stroke and draw it in this context basically. Put it in this context. Okay? So we're not going to talk about that, but same concept. It's just whether you're drawing directly in the context or whether you're building a path first. And why would you build a path first? Maybe you're building a star and you want to put 100 stars up there. You build a star path and then you would put it up there 100 times. All right, so I promised UI color, and here it is. There are some class methods in UI color, like red color, that will return some standard colors. There's about a dozen of them. Red, cyan, black, brown, white, that kind of thing. So you can get that. And of course, there are a number of init methods in UI color that you can create color. So here's one that inits with RGB, and we'll talk about alpha in a second. And so that's straightforward, right? You create a color with RGB. I think there might be HSB in there and some other ways of creating colors. And then you can call set fill like we did before, or set stroke. You can also just call set on a color, and that sets the fill and the stroke. Okay? And that's what UI color is used for, is to set the fills and strokes. The alpha, let's talk about the alpha there. You can draw with transparency in UI view. Okay, it's actually not uncommon to draw with transparency in UI view, but there's some things to think about here. First of all, if you're going to draw with transparency in your view, you're going to use like an alpha. Alpha, by the way, is how transparent it is. So an alpha of 0 means it's completely transparent. It's so transparent you can't see the thing. And 1.0 is fully opaque. In other words, you can't see through the thing. You can only see it covered. It's fully opaque. To draw transparently, you have to set opaque, this property opaque, to no. That's purely a performance optimization. As you can imagine, when iOS is trying to draw all these things, if it knows that things are not transparent, it can do a lot less expensive merging of bits between views that overlap. Right? Understand why that is? So you definitely want to set that to no. Also, think about other things of making transparency for a view besides using alpha colors. For example, you can set the background color of your entire view to be a partially transparent color. Okay? So like, you know, a kind of a red that's kind of see-through, and then your view would show through. The background of it would show through. You also can set the alpha of the whole view, right? So that the whole view, you draw it opaque, let's say, and then you set the alpha to 0.5, and it'll be halfway transparent, the whole view. Right? There's also another thing you can do, which you can set the property hidden. And what hidden says is this view stays in the view hierarchy, but it doesn't draw anything, you know, you don't show it's drawing, and you don't handle any touch events. So it's kind of like it's not even in the view hierarchy, but it still stays there. And hidden is actually somewhat common to use, because you've got small screen real estate on a phone. You've got all these views in there. If a view is not currently useful, then hide it, right? And it won't be on screen, won't be bothering the end user. And then as soon as something happens that makes it so that view matters or is meaningful, you can unhide it, okay? And that's a lot cheaper than trying to set transparency and all that stuff, although it's pretty smart. If you set transparency to 0, it's very similar, actually, to saying hidden, if not identical. Again, remember that this transparency interacts with the order of the subviews, right? The top things in the subview list are in the back, and other things in front. Views, of course, can overlap. They don't have to be like tiled or don't have to be right on top of each other. They can be slightly overlapping. So you can use transparency to great effect, and especially for animation, causing views to fade in, fade out, right? And we're going to talk all about animation later in the class, how to animate your views. But do also understand that transparency is not cheap, okay? Taking two views and combining their bits with transparency is quite a bit more expensive than just taking two overlapping views and picking the bits in the front, okay? So the graphic state, the main graphic state thing you're going to set is color, but you can also set line width and even really complicated things like a fill pattern. You don't have to just fill with a color. That triangle could be filled with a pattern. And there's a whole mechanism for creating a pattern and all that stuff. You can look all that up. It's really outside the scope of this lecture. One thing you have to be a little careful with the graphic state, you got to think about subroutines. Right? Because the way this is working, I got a context, and I'm setting its graphic state, and then I'm doing a stroke or a fill. Well, what if I call a subroutine? And that subroutine wants to set a lot of graphic state. That's messing up the graphic state of the thing that called it. So there's a mechanism for that. It's called pushing and popping the context. So if I had a subroutine called draw green circle, this is just a method that draws a green circle. Notice I know it's going to be used in the state of being a subroutine, so I push the context at the beginning, change the color to green or whatever, line width or whatever, do whatever drawing I want, and then I pop, and that puts the state back to the way it was when the caller called my subroutine, right? And push and pop, very efficient, so you don't have to worry about, it's kind of, I don't want to push it, you know, it's built to be fast. And so if you had your draw rect, here's an example of draw rect, that's going to use that draw green circle. I might have set my color to red, and I'm drawing some stuff in red, and I draw the green circle, and then I want to keep drawing in red. Well, if green circle left it the color green, then my red drawing would start being green. That would be bad. So everyone understand why we do this push-pop thing? It's just for subroutines. And we'll show that in the demo next week, too. All right, drawing text. Normally, you're going to use a UI label if you want to draw text. UI labels are really good at drawing text, and they can draw all kinds of funky things, shadows and all kinds of stuff. So most of the time, you're going to use a UI label. But if your custom view wants to draw its own text, the way it does that is first it has to get a font object, okay, UI font, and you can look at the documentation for how you get a font. You can get a system font, you can get a font by name, etc. And then once you have the font, you actually call a method on NSString to draw. Now, this should be disturbing to you because Foundation, where NSString is not a UI thing. Okay, Foundation is where NSArray and NSDictionary and NSString and NSObject are. There's no drawing. There's no drawing in Foundation. So why are we here? Okay, because string is kind of the obvious place you would want to draw it. You'd want to draw a text. You got the string you want to draw. It'd be nice just to send it a message. So how is this made to work? And the answer is that UIKit, which is a different framework from Foundation, adds these string drawing methods itself. That code is in UIKit, and it adds them to string using a mechanism in Objective-C called categories. Okay? Now, categories is a bit of a Pandora's box, as you can imagine, because UIKit is adding a method to a class in a different framework. We're not talking inheritance here or anything. It's just flat out adding that method. That's kind of weird. And that can be abused, okay, badly. And it also can cause problems where you're trying to add a method that's already implemented in that other class. That would be somewhat of a complication. So we're going to talk about categories. We're actually going to use categories in this class quite extensively because they are really good for what they're good at. Okay, they can be bad when you use them for things they shouldn't be used for, but they can be really good for what they're good at. So we'll talk about that later. So don't worry about that now. But the point is, when you want to draw text, you just send a message to the string, like draw at point with font. So you got your font. You tell it what point you want to draw. Everything is upper left. So this is, the text is going to draw in a certain rectangle depending on the size of the text, and you're specifying the upper left corner. You can also find out the size of that rectangle, what size it's going to be, using size with font. Give it the font, and it'll tell you, oh, that's going to take a rectangle this big to draw that font. Okay? Super straightforward. Everybody got that? Questions? All right, so that's text. How about drawing images? Just like UI label, there's a nice class in iOS called UI image view, which we'll be talking about in the future as well. And UI image view, just like UI label for images, right? You drag it out, you set the image, bam, you got your image. It knows how to scale and resize and all kinds of things. But if you feel like you want to draw that image in your DrawRect, okay, not using another view, then first you got to get an image. And there's quite a few ways to get an image. Probably the common way is to drag it into Xcode, into your resources folder, and then just say image named, and it'll find it in there. Okay, that's the most common way. You can get it out of the file system. Someone might pass it to you over the network as a bag of bits, like NSData right there. We haven't talked about the file system. We haven't really talked too much about NSData, except for that you know it's a bag of bits. You'll see this, how this stuff works later. You can also create your own image, UI image, by drawing with the context things. You do that by doing this UI graphics begin image context, and you press specify size, and then just start drawing. And when you're done, you say UI image my image equals this function, C function UI graphics get image from current context, and you'll have a UI image that represents all that stroking and filling that you did. And then you end the image context, and now you have a UI image. Okay, so there's a lot of ways to get a UI image. And once you have it, the way you draw it in your DrawRect is using these UI image methods. Draw at point, draw rect, draw as pattern in rect. The difference there, draw at point, is going to draw the image at its natural size with that point as the upper left corner. Draw in rect is going to scale the image to that rectangle. Draw pattern in rect is going to keep repeating that image to fill up that rectangle. It's tiled, basically. Okay? So that's images. Just as an aside, you can, if you have a UI image, get its JPEG representation or a PNG representation using these C functions, which is kind of cool. Just gives you a bag of bits. The bits are encoded in either JPEG or PNG. Okay, that's it for views. All right. Tomorrow we have source control. That's going to be really brief. I don't know, maybe only for 15 minutes or so. I'm not going to give a whole lecture on how to manage software in big teams and checking out branches and resolving conflicts. We're not going to talk about that. What I'm going to talk about is what Xcode's UI is if you have your source under source code control. Okay? So it can do things like let you check in changes, show you a history of changes, side by side. It's pretty cool, but it doesn't take a long time to show because, again, I'm only going to show you Xcode's UI of it. Not required for this class, by the way. We're not going to require you to do source control in any of your assignment submissions. Although once you see the lecture tomorrow, or if you play around with source control, you might decide, yeah, actually, it's cool because I can keep track of all the changes, and if I made a mistake, I can go back and look what I did. So that's kind of nice. And then next week, we'll be continuing this whole kind of theme of views and controllers and touch events, etc. First thing, not first thing, but on Tuesday I'll do a lecture where we do a custom UI view, and then we're going to talk about the view controller's lifecycle. So controllers, as I talked about before, can be used as the V in a model view controller, and so you get controllers of controllers. And as these controllers come on screen and go off screen, they get sent messages. Okay, they get warned, you're about to come on screen. Oh, you just came on screen. Oh, you're about to go off screen. You just went off screen. So that you can do things, especially lazily. We don't really want to do things like a database lookup or something like that until we're sure we're actually going to go on screen. Okay? Why waste the processor's time doing something if we're not going to be on screen? So we do a lot of stuff lazily. Just like we did lazy instantiation in our getters, we're going to be doing lazy drawing and stuff like that in these view controller lifecycle methods. And we're also going to talk about storyboarding. You saw the storyboards a little bit so far. We're going to talk about how to use the storyboard mechanism both to build a little more complicated UIs and to hook up our MVCs. And also we're going to show how to use the storyboards to have two separate UIs, okay, for two different platforms in the same app. Universal applications, we call them. Okay, that's all I got. See you next week. Good luck on your homework. If you have any questions, I'm here.
For more, please visit us at Stanford.